Hello there and welcome to the Dreamy Science Channel. I'm so glad you found your way here tonight. Tonight, we're staying close to home in cosmic terms, exploring the 8 magnificent worlds that share our solar system. From scorching surfaces to frozen moons, from diamond rain to backwards rotation, these planets hold secrets that are both fascinating and deeply soothing. If these peaceful explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps other sleepy souls find their way here too, one restful night at a time. Now, settle in comfortably, and let's begin our tranquil tour of the worlds that dance around our sun. Mercury experiences the most extreme temperature swings in the solar system. This small world closest to the sun faces a curious contradiction. During its long day, which lasts about 88 Earth days, Mercury's surface can reach temperatures of over 400 degrees Celsius, hot enough to melt lead. But when night falls on Mercury, temperatures plummet to minus 170 degrees Celsius, colder than anywhere naturally found on Earth. This dramatic swing of nearly 600 degrees happens because Mercury has almost no atmosphere to trap heat. The same lack of air that allows temperatures to soar during the day lets all that heat escape into space during the night. It's a world of extremes, yet there's something oddly peaceful about this simple rhythm of scorching heat and bitter cold, cycling endlessly as Mercury makes its lonely orbit around our star. Venus rotates backwards compared to most other planets. While nearly every planet in our solar system spins in the same direction, Venus chose a different path. It rotates clockwise when viewed from above, the opposite of Earth and most of its planetary siblings. Even stranger, Venus rotates so slowly that its day is longer than its year. One full rotation takes 243 Earth days, while it completes an orbit around the Sun in just 225 Earth days. This means that on Venus, the Sun rises in the west and sets in the east, but so slowly that sunrise and sunset would be separated by months of Earth time. Scientists aren't entirely sure why Venus spins this way. Perhaps it was knocked off course by a massive collision long ago. Or maybe gravitational forces gradually slowed and reversed its rotation over billions of years. Whatever the cause, Venus continues its slow, backwards dance through space. Mars has seasons just like Earth, but each one lasts about twice as long. The red planet tilts on its axis at nearly the same angle as Earth, giving it 4 distinct seasons. However, because Mars takes about 687 Earth days to orbit the Sun, each Martian season stretches for roughly 6 months. Spring on Mars brings dust storms that can engulf the entire planet, while winter sees carbon dioxide snow falling at the polar caps. During summer, temperatures might reach a comfortable 20 degrees Celsius at the equator, but winter nights can drop to minus 140 degrees. The seasonal changes also affect the planet's appearance. The polar ice caps grow and shrink with the seasons, and dust storms migrate across the surface in predictable patterns. For a planet often called barren and lifeless, Mars maintains a surprisingly dynamic and rhythmic seasonal cycle that has persisted for billions of years. Jupiter acts as a cosmic vacuum cleaner for the solar system. This massive planet, with more than twice the mass of all other planets combined, serves as a gravitational guardian for the inner solar system. Its immense pull captures or deflects many asteroids and comets that might otherwise threaten Earth and the other rocky planets. Jupiter's influence reaches far beyond its own space, creating families of asteroids called Trojans that share its orbit, forever trapped in gravitational balance points ahead of and behind the giant planet. Some scientists believe that without Jupiter's protective presence, Earth would have been bombarded with far more asteroids and comets throughout its history, possibly preventing complex life from developing. In this quiet way, Jupiter has been our celestial protector for billions of years, sweeping up debris and keeping the inner solar system relatively peaceful. Its 4 largest moons, discovered by Galileo over 4 centuries ago, continue their eternal dance around this gentle giant, each one a world unto itself. Saturn's rings are surprisingly young and temporary. Those magnificent rings that make recognizable are not Saturn instantly ancient features of the planet. Scientists now believe they formed relatively recently in cosmic terms, perhaps only 100 million years ago, when dinosaurs roamed the Earth. The rings may have formed when an icy moon wandered too close to Saturn and was torn apart by tidal forces, or perhaps when 2 moons collided in Saturn's vicinity. The countless ice particles that make up the rings range in size from tiny crystals to house-sized chunks, all orbiting Saturn in thin, flat sheets. What makes this even more remarkable is that the rings won't last forever. They're slowly spiraling inward towards Saturn, pulled by the planet's gravity and magnetic field. In another 100 million years or so, they'll be gone, consumed by the planet they once adorned. Saturn will continue its stately orbit, but future civilizations will see it as just another ringed world that has lost its crown. For now, we're fortunate to live during the brief cosmic moment when Saturn wears its spectacular jewelry. Uranus rolls on its side like a cosmic bowling ball. While most planets spin upright like tops, Uranus is tipped over so far that its axis of rotation lies almost in the plane of its orbit. This means that instead of spinning like a top, Uranus essentially rolls along its orbital path like a ball rolling down a hill. This extreme tilt, about 98 degrees from vertical, gives Uranus the most unusual seasons in the solar system. For 42 years at a time, one pole faces the sun, while the other experiences continuous darkness. Then, as Uranus continues its 84-year orbit, the seasons gradually shift until the opposite pole faces the sun for the next 42 years. During the brief spring and autumn periods, the sun rises and sets normally across the planet. Scientists think this dramatic tilt resulted from a collision with an Earth-sized object early in the planet's history, an impact so severe it knocked Uranus onto its side. Despite this violent beginning, Uranus now moves peacefully through space, rolling serenely along its orbital path, with its family of 27 known moons accompanying it on this sideways journey. Neptune has winds that blow faster than the speed of sound. The distant blue planet experiences the most powerful winds in the solar system, with speeds reaching up to 2,000 kilometers per hour. These supersonic winds are particularly puzzling because Neptune receives only 1/10,000th of the sunlight that Earth does, providing very little energy to drive such intense weather. The winds blow in the opposite direction of the planet's rotation, adding to the mystery of what powers these atmospheric rivers. Neptune's deep blue color comes from methane in its atmosphere, which absorbs red light and reflects blue wavelengths back to space. The planet also radiates more heat than it receives from the sun, suggesting it has an internal heat source that may help drive its extreme weather. Dark spots, similar to Jupiter's Great Red Spot, occasionally appear in Neptune's atmosphere, but they come and go over periods of several years. These storms can be as large as Earth itself, swirling through the thin air of this distant world. Despite being so far from the Sun that it takes 165 Earth years to complete one orbit, Neptune remains a dynamic and active world. Every planet in our solar system could fit in the space between Earth and the Moon. The distance from Earth to the Moon is about 384,000 kilometers, which seems vast from our perspective. However, if you could line up all the planets in our solar system side by side, they would stretch across only about 370,000 kilometers. This means there would be room to spare, with about 14,000 kilometers left over. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune would all fit comfortably in that seemingly empty space between us and our lunar companion. This comparison helps put the true scale of space into perspective. What appears to be a relatively short distance on the cosmic scale is actually enormous when measured. Set against the worlds we know. The Moon, hanging quietly in our night sky, is separated from us by a gulf wide enough to contain our entire planetary family. Mars has the largest volcano in the solar system. Olympus Mons on Mars stands about 21 kilometers high, nearly 3 times taller than Mount Everest. This massive shield volcano covers an area roughly the size of France and rises so gradually that if you were standing on its slopes, you might not even realize you were on a mountain. The gentle incline averages only about 5 degrees, making it more like a vast, slowly rising plain than a steep peak. Olympus Mons is so large that its base would stretch from New York to Philadelphia, and its summit would extend well into the stratosphere if it existed on Earth. The volcano is thought to be relatively young in geological terms, with some lava flows appearing to be only a few million years old. However, it's likely dormant now, as Mars no longer has the active geology needed to feed such massive volcanic activity. The volcano sits in a region called the Tharsis Volcanic Province, where several other large volcanoes also stand like ancient monuments to Mars's more geologically active past. Venus has surface pressure 90 times greater than Earth's. Standing on the surface of Venus would feel like being nearly a kilometer underwater on Earth. This crushing atmospheric pressure results from Venus's thick atmosphere, which is about 96% carbon dioxide. The dense air creates a runaway greenhouse effect, trapping heat so efficiently that Venus became the hottest planet in the solar system, even though Mercury is closer to the Sun. Surface temperatures on Venus reach about 460 degrees Celsius, hot enough to melt zinc and lead. The atmospheric pressure is so intense that early Soviet landers that reached the surface were crushed within hours. Despite these extreme conditions, There's something almost hypnotic about imagining this world, shrouded in thick, slowly moving clouds of sulfuric acid that completely hide the surface from view. The clouds reflect sunlight so effectively that Venus shines as the third brightest object in our sky after the sun and moon, earning it the name of both the morning star and evening star throughout human history. Jupiter's Great Red Spot is a storm larger than Earth that has been raging for centuries. This massive anticyclonic storm has been continuously observed since the 1600s, though it may have been spinning for much longer. The Great Red Spot is so large that 2 or 3 Earths could fit inside it comfortably, yet it's gradually shrinking. Historical observations show that it was once much larger and more elongated than it is today. The storm's distinctive red color likely comes from complex chemical reactions in Jupiter's upper atmosphere, possibly involving sulfur and phosphorus compounds. Despite its size and longevity, the Great Red Spot is essentially a high-pressure system, similar to hurricanes on Earth, but powered by Jupiter's internal heat and rapid rotation. The storm rotates counterclockwise with wind speeds reaching up to 400 kilometers per hour around its edges. What's particularly fascinating is how this ancient storm has persisted, while countless smaller storms have formed and dissipated around it. Like a permanent whirlpool in Jupiter's turbulent atmosphere, Saturn is less dense than water and would float if placed in a cosmic ocean. Despite being the second largest planet in our solar system, Saturn has such low density that it would actually float if you could find a bathtub large enough to hold it. With a density of only about 7/10 that of water, Saturn is primarily composed of hydrogen and helium in various states. This low density is due to Saturn being essentially a giant ball of gas with no solid surface to stand on. If you could somehow travel into Saturn's atmosphere, you would gradually sink deeper into increasingly dense gas until the pressure became so intense that the hydrogen would behave more like a liquid and eventually like a metal deep in the planet's core. The transition would be so gradual that there would be no ear boundary between the atmosphere and the interior. Saturn's rapid rotation, completing one day in just over 10 hours, causes the planet to bulge noticeably at its equator, making it the most flattened planet in our solar system. This combination of low density and rapid rotation gives Saturn its distinctive oblate shape. Uranus has a magnetic field that tumbles through space like a cosmic somersault. Unlike most planets whose magnetic fields align roughly with their rotation axes, Uranus has a magnetic field tilted 59 degrees away from its rotational axis. Even stranger, this magnetic field doesn't originate from the planet's center, but from about 1/3 of the way toward the surface. As Uranus rolls along its orbital path, its magnetic field tumbles and wobbles through space in a complex corkscrew pattern. This creates a magnetosphere unlike any other in our solar system, one that opens and closes to the solar wind in unpredictable ways. Scientists believe this unusual magnetic configuration results from the same ancient collision that knocked Uranus onto its side, scrambling not just its rotation, but the very structure of its interior. The planet's magnetic field switches on and off as it rotates, creating a lighthouse effect that pulses every 17 hours and 14 minutes. Neptune takes 165 Earth years to complete a single orbit around the Sun. This distant world has only completed one full trip around the Sun since its discovery in 1846. In fact, Neptune didn't finish its first observed orbit until 2011, making it the first planet to reach this milestone since being found. From Neptune's perspective, seasons aren't measured in months but in decades. A single Neptunian season lasts about 40 years, meaning that weather patterns and atmospheric changes unfold over human lifetimes. The planet's distance from the Sun means it receives less than 1% of the sunlight that Earth enjoys. Yet it remains surprisingly active and dynamic. Its deep blue atmosphere contains the fastest winds in the solar system, and storm systems larger than Earth appear and disappear over periods of several years. Despite being so far away that sunlight takes over 4 hours to reach it, Neptune continues its stately dance around our star with mathematical precision. Mercury has ice hiding in the shadows of its polar craters. Despite being the closest planet to the Sun and experiencing surface temperatures hot enough to melt lead, Mercury harbors frozen water in permanently shadowed regions near its poles. These crater floors never see sunlight, creating natural cold traps where temperatures remain below -170 degrees Celsius year-round. Radar observations from Earth and spacecraft have confirmed that these shadowy refugees contain billions of tons of water ice, possibly delivered by ancient comet impacts. The ice may be mixed with organic compounds, creating a dark layer that helps preserve it. Some of these deposits could be billions of years old, having survived in their frozen state since the early days of the solar system. It's a poetic irony that the planet closest to our Sun harbors some of the most ancient and pristine ice in the inner solar system. Locked away in eternal darkness just kilometers from sun-baked plains, Mars experiences dust devils that can tower 7 kilometers high. These whirling columns of dust and debris form when the Martian surface heats unevenly, creating rising columns of warm air that begin to spin. Unlike the small dust devils occasionally seen on Earth, Martian dust devils can grow to enormous proportions, reaching heights of 7 kilometers and lasting for hours as they wander across the rusty landscape. Some are so large they can be seen from space, creating dark tracks across the planet's surface as they sweep up loose dust and sediment. The thin Martian atmosphere, less than 1% as dense as Earth's, allows these dust devils to grow much larger than would be possible on our world. They play an important role in Mars's climate, redistributing dust and heat across the planet's surface. Interestingly, these towering whirlwinds have occasionally cleaned solar panels on Mars rovers, helping to extend their missions by removing accumulated dust that blocks sunlight. Jupiter radiates more heat than it receives from the Sun. This giant planet generates its own warmth from deep within, radiating about 67% more energy than it absorbs from solar radiation. This internal heat source comes from the slow gravitational contraction of the planet itself, a process that has been continuing since Jupiter first formed 4.5 billion years ago. The planet is still slowly shrinking, compressing under its own immense gravity and converting gravitational potential energy into heat. This process causes Jupiter to glow faintly in infrared light, making it warm enough that its cloud tops maintain temperatures of -145 degrees Celsius, despite being over 5 times farther from the Sun than Earth. Without this internal heat source, Jupiter would be much colder and likely have a very different atmospheric structure. The gentle warmth radiating from Jupiter's interior drives the complex circulation patterns in its atmosphere and helps power the storms that have raged in its skies for centuries. Saturn's moon Titan has lakes and rivers of liquid methane and ethane. This fascinating world, larger than the planet Mercury, is the only place in the solar system besides Earth known to have stable liquid on its surface. However, instead of water, Titan's lakes and rivers consist of liquid hydrocarbons like methane and ethane, which remain liquid in the moon's frigid temperatures of -179 degrees Celsius. These hydrocarbon lakes are concentrated mainly near Titan's North Pole, with the largest, called Kraken Mare, being larger than the Caspian Sea on Earth. Titan even has a weather cycle similar to Earth's water cycle, but with methane instead of water. Methane evaporates from the lakes, forms clouds in the thick atmosphere, and falls as methane rain that flows through river channels back to the lakes. The Cassini spacecraft observed seasonal changes in these lakes over its 13-year mission, watching them grow and shrink with Titan's long seasons. Some lakes appear to be temporary, filling during methane storms and then evaporating away, while others seem to be permanent features of this alien landscape. Venus completes its orbit around the Sun faster than it rotates once on its axis. This creates one of the most unusual day-night cycles in the solar system. A Venusian day, measured from sunrise to sunrise, actually lasts 117 Earth days, while a Venusian year is only 225 Earth days. This means that Venus experiences fewer than 2 sunrises per year. The extremely slow rotation, combined with the planet's backward spin, creates long periods of daylight and darkness that each last about Earth days. During 58, the long Venusian day, the thick atmosphere distributes heat so effectively around the planet that there's virtually no temperature difference between the day and night sides. The dense clouds that perpetually shroud Venus circle the planet in just 4 Earth days, moving at speeds of over 300 kilometers per hour in the upper atmosphere, while the planet beneath rotates at a leisurely walking pace. Mars has polar ice caps made of both water ice and frozen carbon dioxide. The southern polar cap contains mostly water ice mixed with dust and rocky debris, creating a permanent ice sheet that persists year-round. The northern cap also contains water ice but is partially covered by seasonal deposits of frozen carbon dioxide, or dry ice, that come and go with the Martian seasons. During the southern hemisphere's winter, carbon dioxide from the atmosphere freezes out at the South Pole, creating a temporary cap of dry ice up to 8 meters thick. As spring arrives, this frozen carbon dioxide sublimes directly back into gas, returning to the atmosphere and revealing the permanent water ice beneath. This seasonal exchange of carbon dioxide between the atmosphere and polar caps causes Mars's atmospheric pressure to vary by about 25% throughout the year. The process creates beautiful spiral patterns and strange formations called spiders, where gas escaping from beneath the dry ice carves channels in the surface. Uranus has 27 known moons, many named after characters from Shakespeare's plays. These moons range from tiny irregular chunks of rock and ice just a few kilometers across to substantial worlds like Titania, which is about half the size of Earth's moon. The 5 largest moons, Miranda, Ariel, Umbriel, Titania, and Oberon, are all named after characters from Shakespeare's plays, while the smaller outer moons bear names from both Shakespeare and Alexander Pope's poetry. Miranda, the innermost large moon, shows evidence of extreme geological activity in its past, with a surface that looks like it was broken apart and reassembled. Some regions of Miranda have cliffs that tower 15 kilometers high, taller than any mountain on Earth. The moons of Uranus orbit in the same plane as the planet's equator, which means they too are tilted on their sides relative to the solar system, creating a unique orbital arrangement found nowhere else among the planets. Neptune's largest moon, Triton, orbits backwards and is slowly spiraling toward the planet. Triton is unusual among large moons because it orbits in the opposite direction to Neptune's rotation, suggesting it was once an independent object, possibly a captured dwarf planet from the outer solar system. This retrograde orbit causes Triton to gradually lose energy and spiral inward toward Neptune. In about 3.5 billion years, Triton will either crash into Neptune or be torn apart by tidal forces to form a spectacular ring system around the planet. Triton is one of the coldest objects in the solar system, with surface temperatures of -235 degrees Celsius. Yet it shows signs of geological activity. The Voyager spacecraft observed geysers of nitrogen gas erupting from Triton's surface, shooting dark material up to 8 kilometers high into the thin atmosphere. These geysers suggest that despite its frigid conditions, Triton has active processes occurring beneath its icy surface, possibly driven by tidal heating from Neptune's gravity. Earth is the only planet in our solar system with plate tectonics. While other worlds show evidence of geological activity, Earth is unique in having a surface broken into large plates that constantly move, collide, and slide past each other. This dynamic process recycles the planet's crust, creates mountain ranges, triggers earthquakes, and plays a crucial role in regulating Earth's climate over geological timescales. The movement of tectonic plates helps maintain the planet's magnetic field by driving circulation in the molten iron core, and it also helps regulate the carbon cycle by burying carbon in ocean sediments and releasing it through volcanic activity. Without plate tectonics, Earth might have ended up like Venus, with a thick carbon dioxide atmosphere and crushing surface pressure. The gentle, continuous motion of these massive rock plates, moving just a few centimeters per year, has shaped our planet's surface for billions of years and continues to slowly reshape continents and ocean basins in an endless dance of geological renewal. Jupiter's moon Europa hides an ocean beneath its icy shell that contains more water than all of Earth's oceans combined. This frozen world, slightly smaller than our moon, conceals one of the most intriguing secrets in the solar system. Beneath its smooth, cracked surface lies a global ocean that may be 50 to 100 kilometers deep, kept liquid by the tidal forces of Jupiter's immense gravity. As Europa orbits the giant planet, these gravitational forces flex and stretch the moon's interior, generating heat that prevents the ocean from freezing solid. The surface ice acts like a protective shell, shielding the hidden sea from the harsh radiation that bathes Jupiter's vicinity. Scientists believe this subsurface ocean may have existed for billions of years, making it one of the most stable aquatic environments in the solar system. The ice above shows strange linear features and chaotic terrain that suggest the ocean below occasionally breaks through to the surface, creating a dynamic interface between the hidden water and the vacuum of space. Venus experiences lightning storms in its sulfuric acid clouds, but they flash in ways unlike anything on Earth. These electrical displays occur in the thick, corrosive atmosphere about 60 kilometers above the planet's surface, where temperatures and pressures are more Earth-like despite the hostile chemistry. The lightning on Venus appears to be less frequent, but potentially more powerful than terrestrial lightning, crackling through clouds made of concentrated sulfuric acid rather than water vapor. Radio signals detected by spacecraft suggest these storms create electromagnetic pulses that can be detected from space. The lightning may play a role in the complex chemistry of Venus's atmosphere, helping to break down molecules and create new compounds in the dense, slow-moving clouds that eternally shroud the planet. Unlike Earth's lightning, which typically lasts for milliseconds, Venusian lightning may persist for longer periods, illuminating the golden twilight world beneath the clouds with brief alien flashes. Mars has auroras, but they appear in unexpected places across the planet, rather than just at the poles. Unlike Earth's auroras, which form beautiful curtains of light near the magnetic poles, Martian auroras can appear anywhere on the planet's surface. This happens because Mars lacks a global magnetic field like Earth's, instead having only localized magnetic patches scattered across its surface, where ancient crustal rocks retain their magnetism from billions of years ago. When charged particles from the solar wind interact with these magnetic anomalies, they create isolated pockets of aurora that glow green, blue, and ultraviolet in the thin Martian atmosphere. These auroras are much fainter than Earth's northern and southern lights, invisible to the human eye, but detectable by sensitive instruments on orbiting spacecraft. The discovery of these scattered auroras helps scientists understand Mars's ancient past, when it likely had a much stronger magnetic field that protected a thicker atmosphere from being stripped away by solar wind. Saturn's hexagonal storm at its north pole is one of the most geometrically perfect features in the solar system. This six-sided cloud formation spans about 30,000 kilometers across, wide enough to fit 4 Earths inside its boundaries. The hexagon has been remarkably stable, maintaining its shape for decades while rotating unit every as a single 10 hours and 39 minutes. Each side of the hexagon is longer than the diameter of Earth, making it a structure of almost incomprehensible scale. Scientists believe this geometric pattern forms due to the interaction of jet streams in Saturn's atmosphere, where different bands of gas moving at different speeds create standing wave patterns that naturally settle into this hexagonal shape. The phenomenon demonstrates how simple physical laws can create unexpectedly ordered structures even in the chaotic environment of a gas giant's atmosphere. At the center of the hexagon lies a hurricane-like vortex with an eye wall similar to storms on Earth, but spinning in Saturn's thick atmosphere of hydrogen and helium. Mercury's core makes up about 75% of the planet's radius, making it the most metal-rich world in the inner solar system. This disproportionately large iron core gives Mercury a magnetic field despite its small size, though it's only about 1% as strong as Earth's. The planet's high density suggests that early in its formation, Mercury may have suffered a catastrophic collision that stripped away much of its rocky mantle, leaving behind a world that is essentially a giant metal ball with a thin, rocky skin. This iron core is partially molten, creating convection currents that generate the planet's weak magnetic field. The extreme temperature variations between Mercury's day and night sides may cause the planet's core to expand and contract slightly, potentially contributing to the formation of scarps and cliffs on the surface. Recent discoveries suggest that Mercury's core may contain sulfur, which would lower its melting point and help explain why parts of it remain liquid despite the planet's small size. Neptune has a dynamic ring system that appears and disappears from different viewing angles. Unlike Saturn's prominent rings, Neptune's rings are faint and uneven, with some sections much brighter than others. These ring arcs, as they're called, seem to come and go over time periods of years or decades. The rings are made of very dark material that reflects only a small percentage of the sunlight that hits them, making them extremely difficult to observe from Earth. The uneven distribution of ring material may be influenced by Neptune's small inner moons, whose gravity helps shepherd particles into clumps and gaps. Some scientists theorize that Neptune's rings are relatively young and temporary features, perhaps created by the destruction of a small moon or the capture of debris from the outer solar system. The rings consist of at least 5 distinct components, named after astronomers who contributed to Neptune's discovery. Venus has mountains that rise 11 kilometers above the mean surface level, taller than Mount Everest. Maxwell Montes, located in Ishtar Terra, stands as the highest peak on Venus and is named after James Clerk Maxwell, the Scottish physicist who developed the theory of electromagnetic radiation. These towering mountains formed through intense volcanic and tectonic activity that occurred when Venus was geologically active billions of years ago. Unlike Earth's mountains, which are often created by colliding tectonic plates, Venus's mountains likely formed from massive volcanic upwelling and crustal deformation. The extreme atmospheric pressure on Venus means that these peaks experience conditions unlike anywhere on Earth, with temperatures hot enough to glow red-hot and atmospheric pressure, res, that would instantly crush any Earth-based mountain climber. The mountains of Venus are composed primarily of basaltic rock, similar to volcanic formations found on Earth's ocean floors, but they've been shaped by the planet's unique evolutionary path. Jupiter's 4 largest moons create a miniature solar system that can be observed with binoculars. Io, Europa, Ganymede, and Callisto, known as the Galilean moons after their discoverer, orbit Jupiter in a complex gravitational dance that has remained stable for billions of years. These moons are tidally locked to Jupiter, meaning they always show the same face to the giant planet, just as our moon does to Earth. Each moon is a world unto itself with distinct characteristics. Io is the most volcanically active body in the solar system. Europa hides its subsurface ocean. Ganymede is the largest moon in the solar system and has its own magnetic field. And Callisto is heavily cratered with an ancient surface that records billions of years of impacts. The orbital periods of the inner three moons, NS, follow a mathematical relationship where Io completes 4 orbits for every 2 of Europa and every 1 of Ganymede, creating a resonant system that helps maintain their orbital stability. Mars has dust storms that can engulf the entire planet and last for months. These global dust storms occur roughly every 3 to 4 Martian years, though smaller regional storms happen much more frequently. When a global dust storm develops, it can obscure the entire planet's surface from view and dramatically alter the atmospheric conditions. The storms begin when strong temperature differences between seasons create powerful winds that lift fine dust particles high into the thin atmosphere. Once airborne, the dust absorbs sunlight and heats the atmosphere, creating more winds and lifting even more dust in a runaway process. These planet-wide storms can last for months, slowly settling as the atmospheric dynamics stabilize and the dust gradually falls back to the surface. The fine Martian dust is so light that it can remain suspended in the atmosphere for weeks, creating a persistent haze that filters sunlight and creates spectacular sunsets with blue hues, the opposite of Earth's red sunsets. Uranus emits almost no excess heat compared to other gas giants in our solar system, while Jupiter and Saturn radiate significantly more energy than they receive from the Sun. Uranus releases almost exactly the same amount of energy it absorbs. This unusual thermal behavior suggests that Uranus lacks a substantial internal heat source, unlike its fellow gas giants. Scientists believe this may be related to the ancient collision that knocked Uranus onto its side, which could have disrupted the planet's internal structure and prevented it from retaining heat from its formation. The planet's core may be cooler than expected, and its interior may be more thoroughly mixed, preventing the gravitational compression that generates heat in Jupiter and Saturn. This thermal equilibrium makes Uranus one of the coldest planetary atmospheres in the solar system, with temperatures dropping to -224 degrees Celsius in its upper atmosphere, colder even than Neptune despite being closer to the Sun. Earth's moon is gradually drifting away from our planet at a rate of about 3.8 centimeters per year. This slow separation occurs due to tidal interactions between Earth and the Moon, where the Moon's gravity creates bulges in Earth's oceans, and the friction from these tidal movements transfers energy from Earth's rotation to the Moon's orbit. As the Moon moves farther away, Earth's rotation gradually slows down, making our days slightly longer over geological time. 4 billion years ago, when the Moon was much closer, Earth's day was only about 6 hours long, and the Moon appeared much larger in the sky. This gradual separation will continue for billions of years until Earth and the Moon become tidally locked, with both always showing the same face to each other. By then, a day and a month will be equal in length, each lasting about 47 current Earth days, and the Moon will appear stationary in Earth's sky. Venus has survived longer without plate tectonics than any other terrestrial planet in our solar system. While Earth's surface is constantly renewed through the movement of tectonic plates, Venus appears to have a mostly static surface that preserves geological features for hundreds of millions of years. This geological stability means that Venus may have experienced catastrophic global resurfacing events in its distant past, where the entire planet's surface was renewed through massive volcanic activity. The planet's surface shows evidence of extensive volcanism, with thousands of volcanic features scattered across its landscape, but most appear to be relatively ancient and inactive. The lack of plate tectonics on Venus may be related to its slow rotation and the absence of water, both of which play important roles in lubricating tectonic movement on Earth. Without the recycling effects of plate tectonics, Venus has retained its dense carbon dioxide atmosphere for billions of years, contributing to its extreme greenhouse effect. Mars experiences seasons in both hemispheres simultaneously due to its elliptical orbit and axial tilt. Unlike Earth, where seasons are primarily controlled by axial tilt, Mars's seasons are significantly influenced by its more elliptical orbit around the Sun. When Mars is closest to the Sun during its orbit, it receives about 40% more solar energy than when it's farthest away. This orbital variation combines with the planet's 25-degree axial tilt to create complex seasonal patterns, where the northern and southern hemispheres experience different intensities of seasons at different times. Southern hemisphere summers on Mars are shorter but more intense than northern hemisphere summers, while southern winters are longer and colder. These orbital and seasonal variations drive the planet's global dust storm cycles and influence the annual exchange of carbon dioxide between the polar ice caps and the atmosphere, creating a dynamic climate system despite the planet's thin atmosphere. Jupiter's magnetic field is about 20,000 times stronger than Earth's and creates the largest structure in the solar system. This immense magnetic field extends far beyond Jupiter's moons, creating a magnetosphere that would appear larger than the full moon if it were visible from Earth. The magnetic field is generated by convection currents in Jupiter's metallic hydrogen core, created by the immense pressure that transforms hydrogen into a conducting fluid. This magnetosphere traps charged particles from the solar wind and from volcanic eruptions on the moon, Io, creating intense radiation belts that would be lethal to unprotected humans. The interaction between Jupiter's magnetic field and the solar wind creates beautiful auroras at the planet's poles, visible in ultraviolet and infrared light. These auroras are hundreds of times more energetic than Earth's northern lights and are fed by a constant stream of particles from Io's volcanoes, making them permanent features of Jupiter's polar regions. Saturn's moon Enceladus shoots geysers of water ice from its south pole into space. These dramatic plumes, first discovered by the Cassini spacecraft, erupt from long fractures in the moon's icy surface called tiger stripes. The geysers contain water vapor, ice crystals, and organic compounds, suggesting that beneath Enceladus's frozen surface lies a warm, salty ocean that may harbor conditions suitable for life. The water from these geysers feeds Saturn's E-ring, creating a tenuous ring of ice particles that extends far beyond Enceladus's orbit. The energy driving these eruptions comes from tidal heating caused by Saturn's gravity, which flexes and warms the Moon's interior as it follows its slightly elliptical orbit. The discovery of hydrothermal activity on Enceladus has made this small moon one of the most promising places in the solar system to search for extraterrestrial life, hidden beneath kilometers of ice in a dark ocean that may have persisted for billions of years. Mercury's day is longer than its year, creating the strangest sunrise schedule in the solar system. A single day on Mercury, measured from noon to noon, lasts about 176 Earth days, while the planet completes its orbit around the Sun in just 88 Earth days. This means that Mercury experiences only 1.5 days during each of its years. The reason for this peculiar timing lies in Mercury's slow rotation combined with its rapid orbital motion. As Mercury moves around the Sun, its orbital motion actually reverses the apparent motion of the Sun in the sky at certain times, causing the Sun to stop, move backward briefly, then resume its forward motion across Mercury's heavens. If you could stand on Mercury's surface, you would witness the Sun rise, grow larger as Mercury approaches its closest point to the Sun, then actually reverse direction and set again before rising once more to continue across the sky. This cosmic dance creates double sunrises and sunsets that occur nowhere else in our solar system. Venus has lightning that may be more powerful than Earth's, crackling through clouds of sulfuric acid. The electrical storms that rage in Venus's upper atmosphere occur about 60 kilometers above the surface, where the crushing pressure gives way to conditions more similar to Earth's stratosphere. These lightning bolts flash through dense clouds composed primarily of sulfuric acid, creating an alien light show invisible from the surface but detectable by orbiting spacecraft. The lightning appears to be triggered by the same basic processes that create thunderstorms on Earth, with rising and falling air masses creating electrical charge separation. However, the chemistry is entirely different, with sulfur compounds playing roles that water vapor fills in Earth's atmosphere. Some scientists theorize that Venus's lightning may be even more energetic than terrestrial lightning, though it occurs less frequently. The electrical discharges may contribute to the complex atmospheric chemistry that maintains Venus's thick, corrosive atmosphere. Mars has 2 tiny moons that race across its sky in opposite directions. Phobos, the larger and inner moon, orbits Mars so quickly that it rises in the west and sets in the east, completing 3 full orbits during a single Martian day. From the surface of Mars, Phobos would appear to zip across the sky in just over 4 hours, looking more like a large, irregular asteroid than a traditional moon. Deimos, the smaller and more distant moon, behaves more conventionally, rising in the east and setting in the west, but takes about 30 hours to cross the Martian sky. Both moons are irregularly shaped chunks of rock that may be captured asteroids, each heavily cratered and dark as charcoal. Phobos orbits so close to Mars that tidal forces are gradually pulling it inward, and in about 50 million miles, billion years, it will either crash into the planet or be torn apart by gravitational forces to form a ring around Mars. Jupiter's great red spot could swallow 2 Earths and still have room for dessert. This massive storm system has been raging in Jupiter's atmosphere for at least 350 years, and possibly much longer. The storm rotates counterclockwise with winds reaching speeds of up to 400 kilometers per hour around its edges. What makes the Great Red Spot so persistent is its position between two jet streams in Jupiter's atmosphere that flow in opposite directions, creating a stable zone where the storm can maintain its structure. The distinctive red color likely comes from complex organic compounds created by lightning and ultraviolet radiation acting on methane, ammonia, and other chemicals in Jupiter's atmosphere. Remarkably, the storm has been gradually shrinking over the past century, though it remains enormous by terrestrial standards. Scientists estimate that at its current rate of contraction, the Great Red Spot might become circular rather than oval within the next few decades. Saturn's rings are made of countless particles ranging from dust grains to house-sized chunks of ice. Each particle in Saturn's rings follows its own independent orbit around the planet, creating the illusion of solid structures when viewed from a distance. The rings are incredibly thin relative to their width, extending over 280,000 kilometers from the planet's surface, but measuring only about 10 meters thick in most places. If you could shrink Saturn's rings to the size of a football field, they would be thinner than a sheet of paper. The rings are divided into several distinct sections, separated by gaps, some created by the gravitational influence of Saturn's moons, which act like cosmic shepherds, keeping ring particles in line. The most prominent gap, called the Cassini division, is maintained by gravitational resonances with Saturn's moon Mimas, which pulls particles out of certain orbital zones. Uranus has rings too, but they're dark and narrow like cosmic hula hoops. Unlike Saturn's bright, wide rings, Uranus's rings are thin, dark, and composed of particles that reflect very little sunlight. These rings were discovered by accident in 1977 when astronomers were observing Uranus pass in front of a star and noticed the starlight dimming briefly before and after the planet blocked it. The rings of Uranus are kept narrow by small shepherd moons that orbit just inside and outside each ring, preventing the particles from spreading out. The ring particles are thought to be made of organic compounds darkened by radiation, giving them their charcoal-like appearance. Some of Uranus's rings are less than 10 kilometers wide, incredibly narrow considering they orbit a planet 50,000 kilometers across. The rings may be relatively young, perhaps formed from the breakup of small moons that wandered too close to Uranus. Neptune's moon Triton has geysers that shoot nitrogen 8 kilometers high into space. These dramatic eruptions occur despite Triton's surface temperature of -235 degrees Celsius, making it one of the coldest places in the solar system. The geysers are powered by a greenhouse effect beneath Triton's thin atmosphere, where transparent nitrogen ice allows sunlight to penetrate and heat darker material below, creating pressure that eventually erupts through the surface. The plumes carry dark particles high into Triton's thin atmosphere, where they're carried by winds before settling back to the surface in long streaks. Triton is the only large moon in the solar system that orbits backwards relative to its planet's rotation, strongly suggesting it's a captured object possibly a dwarf planet from the outer solar system that Neptune gravitationally captured long ago. This backwards orbit causes Triton to gradually spiral inward toward Neptune, and in several billion years, it will either crash into the planet or be torn apart to form spectacular rings. Earth's magnetic field occasionally reverses, with magnetic north becoming magnetic south. These magnetic reversals have occurred hundreds of times throughout Earth's history, with the most happening recent reversal about 780,000 years ago. During a reversal, the magnetic field doesn't simply flip overnight, but gradually weakens, becomes chaotic with multiple magnetic poles appearing around the planet, then eventually reorganizes with the opposite polarity. These reversals are recorded in volcanic rocks and ocean floor sediments, where iron-bearing minerals align with the magnetic field as they cool or settle. The process typically takes several thousand years to complete, during which Earth's protection from cosmic radiation is reduced. Some scientists theorize that magnetic reversals may be linked to climate changes or extinction events, though the evidence remains inconclusive. The next reversal could begin at any time, though predicting exactly when remains impossible. Mercury has scarps that tower kilometers high, created as the planet shrank over billions of years. These massive cliffs, called lobate scarps, formed as Mercury's large iron core gradually cooled and contracted, causing the planet's surface to wrinkle like a raisin. Some of these scarps stretch for hundreds of kilometers across Mercury's surface and rise several kilometers high, creating some of the most dramatic topographical features in the inner solar system. The scarps cut across craters and other geological features, indicating they formed after most of Mercury's heavy bombardment period ended. Recent analysis suggests Mercury may still be shrinking today, though at a much slower rate than in its early history. The planet's surface shows evidence of relatively recent geological activity, with some scarps appearing to be only a few million years old, suggesting that Mercury's interior may still be slowly cooling and contracting. Venus experiences snow on its highest mountains, but it's made of metal rather than water. At elevations above about 2.6 kilometers, Venus's surface becomes cool enough for metallic compounds to condense out of the hot atmosphere and fall as a kind of metallic frost. This snow is likely composed of bismuth sulfide and lead sulfide, heavy metal compounds that can exist as vapors in Venus's scorching lower atmosphere, but condense into solid particles at the slightly cooler temperatures found at high altitude. The metallic snow gives Venus's highlands a bright, reflective appearance when observed by radar from spacecraft, creating shimmering peaks that stand out against the planet's generally dark surface. This phenomenon occurs because Venus's thick atmosphere creates such intense greenhouse heating that even compounds we consider solid metals can exist as gases near the surface. Mars has seasons that affect the entire planet's atmospheric pressure as carbon dioxide freezes and thaws at the poles. During winter in each hemisphere, so much carbon dioxide freezes out of the atmosphere onto the polar ice cap that the planet's overall atmospheric pressure drops by about 25%. This seasonal exchange of atmospheric gases creates weather patterns and wind systems that are driven as much by the change in pressure as by temperature differences. When spring arrives, and the frozen carbon dioxide begins to sublime back into gas, it creates powerful winds and dust storms as the atmosphere rushes to rebalance itself. The process also creates strange seasonal features like dark fan-shaped markings near the South Pole, where escaping carbon dioxide gas carries dark dust particles across the bright ice cap. This global atmospheric breathing gives Mars a dynamic climate despite having an atmosphere less than 1% as thick as Earth's. Jupiter's moon. Io has over 400 active volcanoes, making it the most volcanically active world in the solar system. These volcanoes spew sulfur and sulfur dioxide hundreds of kilometers into space, creating colorful plumes that can be seen by spacecraft from great distances. The volcanic activity is powered by tidal heating from Jupiter's immense gravity, which constantly flexes and stretches Io's interior as it orbits the giant planet. This tidal kneading keeps Io's interior molten and drives continuous volcanic eruptions that completely resurface the moon every million years or so. The volcanoes create a constantly changing landscape of lava lakes, sulfur flows, and towering volcanic peaks. Some of Io's volcanic plumes reach heights of 500 kilometers, creating umbrella-shaped clouds of sulfur particles that eventually fall back to the surface, painting the moon in brilliant yellows, reds, and oranges. The volcanic activity also creates a donut-shaped cloud of sulfur particles that follows Io's orbit around Jupiter. Saturn's moon Titan has weather patterns including methane rain, rivers, and seasonal lake systems. This remarkable world experiences a methane cycle similar to Earth's water cycle, but at temperatures cold enough to keep methane liquid. Seasonal methane storms create downpours that fill temporary lakes and rivers, which then evaporate back into the atmosphere or flow into larger permanent lakes. The changing seasons on Titan, each lasting about 7 Earth years, cause these weather patterns to migrate between the northern and southern hemispheres. During northern spring and summer, storms develop around the North Polar region, while the south experiences drier conditions. The methane rain creates river channels and erosion patterns remarkably similar to those created by water on Earth, demonstrating how the same physical processes can operate with entirely different materials under a lit en condition. Uranus experiences the most extreme seasonal changes in the solar system due to its sideways orientation. For 42 years at a time, one pole faces toward the sun while the other remains in darkness, creating seasons unlike anywhere else. During these extreme seasons, one hemisphere experiences continuous daylight while the other endures decades of night. The transition periods, when the sun rises and sets normally across the planet, last only a few years before the next 42-year period of extreme seasons begins. This unusual seasonal pattern affects the planet's atmosphere in complex ways, with heat slowly redistributing from the sunlit hemisphere to the dark one over decades. The atmospheric response to these extreme seasons is still not fully understood, as Uranus has only been observed for a fraction of its 84-year orbital period since its discovery. Neptune's deep blue color comes from methane in its atmosphere, which absorbs red light and reflects blue wavelengths back to space. However, Neptune appears bluer than Uranus, despite both planets having similar amounts of methane. suggesting there's an additional component in Neptune's atmosphere that enhances its blue coloration. Scientists suspect this may be an unknown compound, or perhaps hazes of hydrocarbons created by the interaction of methane with solar radiation. The planet's dynamic atmosphere constantly creates and destroys cloud features, with bright methane clouds appearing at high altitudes where the gas freezes into ice crystals. These clouds cast shadows on the deeper atmosphere below, creating a layered appearance that changes over time scales of hours to days. Earth is the only planet where water can exist naturally in all three phases: solid, liquid, and gas at the same time and place. This unique property occurs because Earth's atmospheric pressure and temperature range allow water to exist at its triple point, where ice, liquid water, and water vapor can coexist in equilibrium. This characteristic is crucial for Earth's climate system and the existence of life as we know it. The water cycle, driven by solar energy, continuously moves water between oceans, atmosphere, and ice caps, distributing heat around the planet and creating the moderate climate that supports life. No other planet in our solar system has conditions that allow a similar cycle with any substance, making Earth's water cycle a unique feature among known worlds. Mercury's surface is covered with a fine layer of dust, created by billions of years of meteorite impacts and solar wind bombardment. This powdery regolith, similar to lunar soil but with different composition, covers the planet's rocky surface and records the history of impacts from asteroids and comets. The lack of atmosphere means that even tiny meteorites that would burn up in Earth's atmosphere reach Mercury's surface, constantly gardening the soil and creating new dust. The solar wind, a stream of charged particles from the sun, also strikes Mercury's surface directly, gradually breaking down rock minerals into fine particles. This process of space weathering has been ongoing for billions of years, creating a layer of dust that may be several meters thick in some places. Venus rotates so slowly that its winds in the upper atmosphere circle the planet faster than the planet itself rotates. While Venus takes 243 Earth days to complete one rotation, the winds in its upper atmosphere race around the planet in just 4 Earth days, creating a phenomenon called super-rotation. These high-altitude winds reach speeds of over 300 kilometers per hour, far faster than any winds on Earth. The mechanism driving this super-rotation is still not fully understood, but it may involve the absorption of solar radiation by sulfuric acid clouds and the subsequent transfer of momentum between different atmospheric layers. This creates a situation where the atmosphere essentially decouples from the solid planet below, spinning much faster than the surface. Mars has impact craters that preserve a record of heavy bombardment from the early solar system. The southern hemisphere of Mars is heavily cratered, indicating it's an ancient surface that has remained relatively unchanged for billions of years. These craters tell the story of the late heavy bombardment, a period about 4 billion years ago when the inner solar system experienced intense asteroid and comet impacts. Some Martian craters are so large they affect the planet's overall shape, with the Hellas Basin being over 2,000 kilometers across and 9 kilometers deep. The preservation of these ancient scars is possible because Mars lacks the active geology and thick atmosphere that would erase such features on Earth. Each crater is like a time capsule, preserving evidence of cosmic events that occurred when the solar system was young and chaotic. Jupiter's 4 largest moons each show the influence of the giant planet's gravity in different ways. Io's volcanic activity, Europa's subsurface ocean, Ganymede's magnetic field, and Callisto's ancient surface all result from their gravitational relationship with Jupiter. The inner moons experience stronger tidal forces, while the outer moons are more influenced by Jupiter's magnetic field and radiation environment. These 4 worlds demonstrate how a single massive planet can create an entire family of diverse satellites, each shaped by its unique position in Jupiter's gravitational well. The systematic differences between the moons provide insight into how satellite systems form and evolve around giant planets throughout the universe. Saturn's largest moon, Titan, has an atmosphere thicker than Earth's, composed primarily of nitrogen with traces of methane and other hydrocarbons. This thick atmosphere creates a substantial greenhouse effect that keeps Titan's surface temperature at about -179 degrees Fahrenheit degrees Celsius, much warmer than it would be without atmospheric warming. The atmosphere is so thick that the surface pressure is about 50% higher than Earth's sea level pressure. Titan's atmosphere also creates weather phenomena, including clouds, precipitation, and seasonal changes that drive the methane cycle. The thick haze in the upper atmosphere gives Titan its characteristic orange appearance and completely obscures the surface in visible light, requiring radar and infrared observations to study the landscape below. And so, as these distant worlds continue their ancient orbits around our Sun, each one maintaining its own rhythm in the cosmic dance, we find ourselves part of this same solar family. Each planet, from scorching Mercury to distant Neptune, follows the same fundamental laws of physics, while expressing them in wonderfully different ways. Their stories unfold over billions of years, yet each moment of their existence adds another page to the grand narrative of our solar system. Uranus has auroras that tumble and twist in ways unlike any other planet. While Earth's northern and southern lights form predictable curtains and arcs near the magnetic poles, Uranus creates auroral displays that spiral and corkscrew through its tilted magnetic field. These ethereal light shows occur when charged particles from the solar wind interact with the planet's unusual magnetosphere, which tumbles through space as the planet rolls along its orbital path. The auroras appear as shifting, ghostly glows that migrate across different parts of the planet as its magnetic field orientation changes with rotation. Because Uranus is tilted on its side, these auroras don't follow the familiar patterns seen on other worlds. Instead, they create a constantly changing light show that dances through the planet's hydrogen and helium atmosphere in ways that would appear alien and beautiful to any observer. Neptune's magnetic field is tilted 47 degrees from its rotation axis and offset from the planet's center. This unusual configuration suggests that Neptune's magnetic field originates not from its core, but from electrical currents in the planet's mantle, where water, methane, and ammonia exist under extreme pressure. The offset and tilted nature of the field creates a complex magnetosphere that wobbles and shifts as Neptune rotates. When the Voyager spacecraft flew by Neptune, it detected radio emissions that varied in unexpected ways, indicating that the magnetic field structure is far more complex than the neat dipole fields found around Earth or Jupiter. This magnetic complexity may be related to the unique internal structure of ice giant planets, where exotic forms of matter exist under conditions impossible to recreate on Earth. Mars once had a much thicker atmosphere that could have supported liquid water on its surface. Evidence suggests that early Mars had atmospheric pressure several times thicker than today, warm enough and dense enough to allow rivers, lakes, and possibly even oceans to exist. This ancient atmosphere was gradually stripped away by solar wind because Mars lacks a global magnetic field strong enough to protect it. The process took place over hundreds of millions of years, slowly transforming Mars from a potentially habitable world into the cold, dry desert we see today. Valley networks carved by ancient rivers, lakebed sediments, and mineral formations that require liquid water all point to a very different Mars in its early history. The planet's polar ice caps and subsurface permafrost reserve remnants of this ancient water, locked away in frozen form. Jupiter's moon. Ganymede is the largest moon in the solar system and has its own magnetic field generated by a molten iron core. This massive moon, larger than the planet Mercury, creates its own magnetosphere that carves out a bubble within Jupiter's much stronger magnetic field. Ganymede's magnetic field suggests it has a differentiated interior with a liquid iron core, making it more like a small planet than a typical moon. The interaction between Ganymede's magnetic field and Jupiter's creates auroras at Ganymede's poles, making it the only moon known to have its own northern and southern lights. The magnetic field may also help protect any subsurface ocean that might exist beneath Ganymede's icy surface, shielding it from Jupiter's intense radiation environment. This magnetic shielding could make Ganymede's hidden ocean more stable and potentially more hospitable than those of other icy moons. Saturn's moon Mimas has a crater so large, it makes the moon look like the Death Star from science fiction. The Herschel crater spans 130 kilometers across, about 1/3 the diameter of the tiny moon itself. The impact that created this enormous crater nearly shattered Mimas completely, and fractures from the collision can be seen on the opposite side of the moon. Despite its small size, only about 400 kilometers across, Mimas plays an important gravitational role in Saturn's ring system. The moon's orbital resonance with ring particles helps maintain the Cassini division, the prominent gap in Saturn's rings. Mimas completes exactly 2 orbits for every 1 orbit of ring particles at the Cassini division, creating a gravitational tug that prevents particles from occupying that region of space. Venus has tessera terrain, mysterious highland regions, with complex patterns that suggest the planet's surface has been folded and fractured by intense geological forces. These areas, which make up about 8% of Venus's surface, show intricate networks of ridges and valleys that intersect at various angles, creating patterns unlike anything seen on Earth or other planets. The tessera formations may represent Venus's oldest surviving surface features, possibly dating back billions of years to when the planet had very different geological conditions. Some scientists theorize that tesserae formed when Venus had a thinner atmosphere and different internal dynamics, preserving ancient crustal deformation in these highland refuges. The complex patterns suggest that Venus once experienced tectonic forces that stretched, compressed, and twisted its surface in multiple directions over long periods of time. Mercury has a tenuous atmosphere called an exosphere, made up of atoms knocked off its surface by solar wind and meteorite impacts. This incredibly thin atmosphere contains oxygen, sodium, hydrogen, helium, and potassium, but it's so sparse that the entire atmosphere weighs less than a small truck. The atoms in Mercury's exosphere don't collide with each other as they do in thicker atmospheres, instead following ballistic trajectories like tiny satellites around the planet. Solar radiation pressure and the solar wind constantly strip away these atoms, so the exosphere is continuously replenished by impacts and solar wind bombardment of the surface. The composition varies with Mercury's position in its orbit, as different surface materials are vaporized when the planet is closest to the Sun. This ghostly atmosphere creates a faint tail of sodium atoms that streams away from Mercury, visible only with specialized telescopes. Mars has recurring slope lineae, dark streaks that appear and fade seasonally on steep crater walls and canyon sides. These mysterious features darken during warm seasons and fade during cold periods, suggesting they involve some kind of fluid flow. The streaks appear on sun-facing slopes where temperatures rise above the melting point of ice, leading scientists to propose they might be caused by briny water seeping from subsurface sources. The water would be extremely salty to remain liquid at Martian temperatures and pressures, creating seasonal flows that darken the soil before evaporating or soaking in. Alternative explanations suggest the streaks might be caused by dry granular flows or seasonal changes in surface minerals. These enigmatic features represent some of the most dynamic processes currently active on Mars, providing clues about water activity on the planet today. Jupiter's radiation environment is so intense that it would quickly damage unshielded electronics and prove lethal to unprotected humans. The planet's powerful magnetic field traps charged particles from the solar wind and from volcanic eruptions on Io, creating radiation belts thousands of times more intense than Earth's Van Allen belts. Spacecraft venturing close to Jupiter must be specially hardened against radiation, with sensitive electronics housed in titanium vaults to protect them from the energetic particles. The radiation is strongest near Io's orbit, where sulfur and oxygen ions from the Moon's volcanoes become trapped and accelerated to high energies. This radiation environment sculpts the surfaces of Jupiter's inner moons, breaking down water ice and creating the exotic chemice try-observe thin in their atmospheres. Even Jupiter's outermost large moon, Callisto, receives radiation doses that would be dangerous to human explorers. Saturn's rings have spokes, mysterious radial features that appear and disappear in the ring system with Saturn's rotation period. These ghostly structures were first observed by the Voyager spacecraft and appear as dark or bright radial streaks extending across thousands of kilometers of ring material. The spokes seem to be composed of tiny dust particles that become electrically charged and levitate above the main ring plane, possibly due to interactions with Saturn's magnetic field or impact events. They appear most commonly when Saturn's magnetic field is tilted at certain angles relative to the Sun, suggesting that electromagnetic forces play a role in their formation. The spokes rotate with Saturn's magnetic field rather than following the orbital motion of ring particles, indicating they're controlled by forces other than simple gravity. These ephemeral features add another layer of mystery to Saturn's already complex ring system. Uranus has a core that may be partly liquid water, ammonia, and methane under extreme pressure and temperature. Unlike the rocky cores of terrestrial planets or the metallic hydrogen cores of gas giants, Uranus likely has what's called an ice core, though the materials would behave more like hot, dense fluids under the extreme conditions deep inside the planet. This exotic core may be surrounded by a mantle of water, methane, and ammonia ices in various phases, topped by an atmosphere of hydrogen and helium. The unusual composition and structure of ice giants like Uranus represent a different class of planet formation, where materials that form as ices in the outer solar system dominate the planet's bulk composition. Understanding the interior structure of Uranus helps scientists model how planets form in the cold outer regions of planetary systems, both in our solar system and around other stars. Neptune has the most dynamic atmosphere of any planet, despite receiving the least solar energy. The planet's active weather system produces the fastest winds in the solar system, massive storm systems, and rapidly changing cloud patterns, all powered by internal heat rather than solar radiation. Neptune radiates 2.6 times more energy than it receives from the Sun, indicating a powerful internal heat source that drives its atmospheric dynamics. This internal energy may come from gravitational contraction as the planet slowly shrinks, or from radioactive decay in its core, or from the gradual separation of helium and hydrogen in its interior. The combination of internal heating and rapid rotation creates jet streams and storm systems that dwarf anything seen on Earth, demonstrating how planetary atmospheres can remain active even in the cold outer reaches of the solar system. Earth's magnetic field has wandered throughout history, with the magnetic poles moving continuously at rates of up to 60 kilometers per year. Currently, the North Magnetic Pole is moving rapidly from northern Canada toward Siberia, accelerating from about 10 kilometers per year a century ago to over 50 kilometers per year today. These movements are caused by changes in the flow patterns of molten iron in Earth's outer core, which generates the magnetic field through a complex dynamo process. The magnetic field also varies in strength, having weakened by about 10% over the past century and 50 years. Paleomagnetic records show that the field has reversed hundreds of times throughout Earth's history, with the magnetic north and south poles switching places. During these reversals, the magnetic field becomes complex and chaotic, before reorganizing with opposite polarity. Mercury's orbit precesses, or shifts, slightly more than Newton's laws predict, an effect that helped confirm Einstein's theory of general relativity. The planet's elliptical orbit rotates slowly around the Sun by about 43 arcseconds per century, more than classical physics can account for. This tiny discrepancy, first noticed in the 1800s, remained unexplained until Einstein's general relativity provided the answer. The effect occurs because Mercury orbits deep in the Sun's gravitational field, where the curvature of space-time becomes significant. This relativistic precession has been measured with extraordinary precision and continues to serve as one of the most elegant confirmations of Einstein's theory. Similar effects occur with all planets, but they're most noticeable with Mercury due to its proximity to the Sun and highly elliptical orbit. Venus may have had oceans for billions of years before its runaway greenhouse effect took hold. Climate models suggest that early Venus, with a slower rotation and different atmospheric composition, could have maintained liquid water on its surface for up to 2 billion years after its formation. During this period, Venus might have been habitable, with temperatures and pressures similar to early Earth. The transition to its current hellish conditions may have occurred gradually, as increasing solar luminosity and volcanic outgassing built up carbon dioxide in the atmosphere. Once the greenhouse effect became self-reinforcing, Venus's oceans would have evaporated, with water vapor escaping to space and leaving behind the dense, dry atmosphere we observe today. This dramatic climate evolution makes Venus a cautionary example of how planetary atmospheres can undergo irreversible changes. Mars has unique geological features called chaos terrain, vast areas where the surface appears to have collapsed into jumbled blocks and mesas. These regions, such as Ionian chaos and Aurora chaos, may have formed when underground ice or water suddenly melted and drained away, causing the overlying terrain to collapse catastrophically. The chaotic landscape consists of randomly oriented blocks of ancient terrain separated by flat-floored depressions that may once have been temporary lakes or seas. Some chaos regions appear to be the source areas for enormous flood channels that carved their way across the Martian surface, carrying volumes of water comparable to the Mediterranean Sea. The formation of chaos terrain represents some of the most dramatic geological events in Martian history. In evolving the rapid release of vast quantities of subsurface water that may have temporarily thickened the planet's atmosphere and warmed its climate, Jupiter acts as a cosmic timekeeper, with its regular orbital period helping to stabilize the orbits of other planets in the solar system through gravitational resonances. The giant planet's massive gravitational influence creates zones of stability and instability throughout the solar system, shepherding asteroids into families and preventing planetary orbits from becoming chaotic over billions of years. Jupiter's position and mass help maintain the relatively circular orbits of the inner planets, including Earth, creating the stable conditions necessary for life to develop and persist. Computer simulations show that without Jupiter's gravitational influence, the inner solar system would be far more chaotic, with planets potentially colliding or being ejected from the system entirely. This gravitational architecture makes Jupiter not just the king of planets, but also the guardian of planetary stability. Saturn's moon. Iapetus has a mysterious equatorial ridge that makes it look like a walnut, rising up to 20 kilometers above the surrounding terrain. This unique feature circles almost exactly around the moon's equator for over 1,300 kilometers, creating one of the most distinctive shapes in the solar system. The ridge may have formed when Iapetus was spinning much faster in its early history, causing material to accumulate at the equator. Or it might be the remnant of a collapsed ring system that fell onto the Moon's surface. Iapetus also has a striking two-tone coloration, with one hemisphere much darker than the other, possibly due to the accumulation of dark material from other moons or interplanetary dust. The combination of the equatorial ridge and contrasting hemispheres makes Iapetus one of the most visually striking objects in the outer solar system. Uranus and Neptune are classified as ice giants rather than gas giants because they contain much larger proportions of water, methane, and ammonia ices in their composition. While Jupiter and Saturn are primarily hydrogen and helium, the ice giants formed in the outer regions of the solar nebula, where these volatile compounds could condense into solid particles. This compositional difference affects everything from their internal structure to their magnetic fields and atmospheric dynamics. Ice giants represent a different pathway of planet formation, where solid materials played a more important role in building planetary mass. The study of ice giants helps scientists understand how planetary systems form in the cold outer regions around stars, and similar worlds may be common around other stars, where conditions favor the condensation of volatile compounds into planetary building blocks. Neptune's largest moon, Triton, may be a captured Kuiper Belt object that was gravitationally snatched by the planet billions of years ago. Triton's retrograde orbit, unusual composition, and similarity to Pluto suggest it originated in the outer solar system before being captured by Neptune's gravity. The capture process would have been violent, possibly disrupting Neptune's original moon system and heating Triton's interior through tidal forces. This heating may have created the subsurface ocean that likely exists beneath Triton's icy surface today, kept liquid by radioactive decay and residual tidal heating. Triton's capture represents one of the most dramatic examples of gravitational interaction in the solar system, demonstrating how giant planets can reshape their local environments by capturing passing objects from the outer solar system. Earth's atmosphere has evolved dramatically over geological time, from an early reducing atmosphere to the oxygen-rich mixture that supports complex life today. The first atmosphere was likely stripped away by solar wind, replaced by volcanic outgassing that created a secondary atmosphere rich in carbon dioxide, water vapor, and other gases. The appearance of photosynthetic organisms fundamentally changed atmospheric composition by producing oxygen as a waste product, eventually leading to the oxygen-rich atmosphere that enables complex multicellular life. This atmospheric evolution continues today, with human activities now significantly influencing atmospheric composition for the first time in Earth's history. The delicate balance of gases that makes Earth habitable required billions of years to achieve and demonstrates the complex interplay between geological and biological processes. Mercury's surface shows evidence of past volcanic activity in the form of smooth plains that filled large impact basins billions of years ago. These volcanic plains, similar to the lunar Maria, formed when the planet's interior was still hot enough to produce basaltic magma that erupted onto the surface. The volcanic activity appears to have ended early in Mercury's history, as the planet's small size caused it to cool quickly and lose its internal heat source. Some of the volcanic plains show unusual compositions with higher concentrations of sulfur than typical basaltic rocks, suggesting that Mercury's interior has a unique chemical composition. The rapid cooling and contraction of Mercury's interior created the massive scarps that cut across these ancient volcanic plains, providing a record of the planet's thermal evolution over billions of years. Venus experiences extreme atmospheric superrotation, where the entire atmosphere circles the planet in just 4 Earth days, while the solid planet takes 243 days to rotate once. This creates wind speeds of over 300 kilometers per hour in the upper atmosphere, far exceeding any winds on Earth. The mechanism driving this superrotation involves complex interactions between solar heating, atmospheric circulation, and the planet's slow rotation. But the exact processes remain one of the great mysteries of planetary science. The super-rotating atmosphere transports heat efficiently around the planet, which is why there's virtually no temperature difference between Venus's day and night sides, despite the planet's extremely slow rotation. This atmospheric behavior makes Venus unique among all known planets, and demonstrates how atmospheric dynamics can become decoupled from planetary rotation under extreme conditions. And as we drift deeper into the gentle embrace of sleep, these worlds continue their eternal dance around our sun, each one a testament to the beautiful diversity that emerges from the same fundamental laws of physics and chemistry. In the vast silence of space, they follow their appointed paths with mathematical precision, carrying with them billions of years of history written in stone, ice, and gas. Their stories interweave to form the larger narrative of our solar system, a tale of formation and evolution that began 4.5 billion years ago and continues to unfold with each passing moment. These worlds remind us that even in the cold depths of space, change happens slowly and peacefully. Mars continues its patient seasonal breathing, exchanging carbon dioxide between its poles and atmosphere in a rhythm that has persisted for eons. Jupiter's great red spot keeps spinning, a storm so ancient it may have been raging when the first complex life appeared on Earth. Saturn's rings catch sunlight and cast shadows, their countless ice particles following orbits so precise they create gaps and divisions that have remained stable for millions of years. Venus rotates backward through its dense golden twilight, where a day unfolds over months and the sun rises in the west. Mercury races around the sun, its cratered surface alternately baking and freezing in temperature swings that would shatter most materials. Yet the little planet endures, unchanged for billions of years. Uranus rolls on its side like a cosmic bowling ball, its seasons lasting decades while its rings and moons accompany it on this sideways journey through space. Neptune churns with the fastest winds in the solar system, powered by heat from deep within the planet rather than the distant sun. Its deep blue atmosphere hosts storms larger than Earth itself, swirling and dissipating over years, while the planet maintains its stately 84-year orbit in the outer darkness. These distant worlds receive so little sunlight, they exist in perpetual twilight, yet they remain dynamic and alive with motion. Each planet carries within it the memory of the solar system's formation, when a cloud of gas and dust slowly collapsed under its own gravity 4.5 billion years ago. The rocky inner worlds formed from the collision and accretion of countless smaller bodies, their surfaces scarred by impacts that recorded the violent early history of planetary formation. The outer giants grew by capturing vast amounts of gas from the solar nebula, becoming massive enough to hold thick atmospheres and families of moons. The asteroid belt between Mars and Jupiter preserves fragments from this early period, countless rocky bodies that never quite managed to form a planet due to Jupiter's gravitational influence. These asteroids range in size from tiny pebbles to dwarf planets hundreds of kilometers across, each one a time capsule from the solar system's youth. Some contain water ice and organic compounds that have been building blocks of life that may delivered to Earth by similar objects early in its history. Beyond Neptune lies the Kuiper Belt, a region populated by icy bodies that formed in the cold outer reaches of the solar nebula. Pluto, once considered the 9th planet, is the largest known member of this distant population. These frozen worlds preserve the original materials from which the solar system formed, largely unchanged by the heat and collisions that shaped the inner planets. They orbit in the perpetual cold and darkness of the outer solar system, receiving so little sunlight that noon appears no brighter than deep twilight on Earth. Even farther out, the Oort cloud forms a vast spherical shell of comets surrounding the entire solar system at distances so great that the Sun appears as just another star. These ancient ice balls occasionally fall inward toward the Sun, developing the glowing tails that make them visible from Earth as they approach the inner solar system. When we see a comet, we're witnessing material that may be older than the planets themselves, pristine remnants neighborhood, that from the very beginning of our cosmic sun itself continues to burn steadily at the center of this vast system, fusing hydrogen into helium in its core and radiating the energy that powers weather, ocean currents, and life on Earth. Our star is middle-aged by stellar standards, about halfway through its 10 billion year lifespan. It will continue shining steadily for another 5 billion years before gradually swelling into a red giant, eventually shedding its outer layers and leaving behind a white dwarf star no larger than Earth. But for now, in this cosmic moment, everything remains in perfect balance. The planets maintain their orbits through the delicate interplay of gravitational forces that have kept the solar system stable for billions of years. Each world contributes to this gravitational symphony, from tiny Mercury's rapid orbit to distant Neptune's stately progression through space. The system is so finely tuned that computer simulations can accurately predict planetary positions millions of years into the future. And now, as these 8 worlds continue their quiet journeys through the darkness, we find ourselves drifting toward rest alongside them. From Mercury's scorching days to Neptune's distant blue storms, each planet holds its own peaceful rhythm, its own gentle secrets whispered across the vastness of space. Tonight, you've traveled with them through seasons that last decades, storms larger than continents, and moons that hide ancient oceans beneath shells of ice. Let their steady orbits carry you into sleep, knowing that somewhere above, these celestial companions continue their eternal dance around our sun, patient and serene in the cosmic night. Sweet dreams.